Hi guys, I'm Jackie. I'm a postgrad student here at Curtin. We hear you've been having some issues with bonding and polarity. So we're here at the new Curtin Resources and Chemistry Precinct where we're going to be talking to Professor Mark Buntine, who's an expert on that kind of stuff, and hopefully that'll help some problems that you guys have been having.
G'day guys, my name's Professor Mark Buntine and I work in the Chemistry Department at Curtin University. One of my jobs is to teach first year chemistry students about theories of chemical bonding, and I'm recording this today to help you guys a little bit in the bonding theories that you need to understand in your Year 12 curriculum. Many students get confused with bonding theories in chemistry because they think that the different theories are indeed different. But the important point to understand is that all of the bonding theories are underpinned with the principles of electrostatics. We have positively charged nuclei consisting of protons and neutrons, and we have negatively charged electrons. And it's the interaction between the positive and the negatively charged species that underpin all of the bonding theories that you need to understand in your Year 12 curriculum. I'm going to start today by talking about some covalent bonding, and I will then go into some of the other theories, and you will see as we progress that it's the same underlying electrostatic principles that will apply to everything. The most commonly found form of bonding and the most commonly description that we have is called covalent bonding. And you would know that term in terms of sharing of electron density. One of the analogies that I like to use is to think of the nuclei, the atoms, as being the bricks in a brick wall. And the electrons, in a covalent sense, are the cement or the mortar that holds those bricks together. If you don't have the cement and you just stack the bricks up, they're not very stable and they will fall apart. So we have a covalent bond consisting of positively charged nuclei with the negatively charged electrons shared between them, holding the nuclei together. And the overall stability of the molecule comes from the balance between the attraction between the negative electrons and the positive nuclei, coupled with the repulsion of the positive nuclei and the repulsion of the negative electrons themselves. Those three terms coupled together give the overall molecular stability, but it's the attraction between the electrons and the nuclei that drive the overall molecular shape and structure. In most cases, the sharing of electron density between atoms in a molecule is not even. That is because most chemical bonds involve different atoms to make up that constituent bond. As chemists, we can understand how the sharing of electron density is unequal by invoking a concept known as electronegativity. Electronegativity is a concept that gives an indication of the ability of an atom to draw electron density to itself. And in the electronegativity concept, the scale increases from the lower left to the upper right of the periodic table. Therefore, fluorine is the most electronegative atom in the periodic table, and elements in the first period, including sodium and the like, are the least electronegative. As a result, in a small molecule like hydrogen fluoride, or HF, the fluorine atom draws the electron density towards itself away from the hydrogen, which is less electronegative. As such, more of the electron density is on the fluorine atom, and we have a slightly negative end of the molecule and a slightly positive end of the molecule where the electron density is less. This is the concept of a polar bond, which I'll talk about again a little bit later on. So what happens when the unequal sharing of electrons between atoms in a molecule becomes extreme? For example, the halogens on the right-hand side of the periodic table are extremely electronegative and will accept electron density readily. On the left-hand side of the periodic table, the alkali metals and the alkali earths are electropositive, and they're perfectly happy to give up their electron density. Under these circumstances, rather than talking about the unequal sharing of electron density, it becomes more appropriate to talk about the formal transfer of an electron from the electropositive to the electronegative species. So, for example, a sodium atom gives up an electron to become a sodium cation. And a halogen, for example, a chlorine atom, readily accepts that electron to become a chloride anion. This alternating three-dimensional array of positive and negative charges is described as ionic bonding. And because we come back to the idea of the electrostatic attraction between positive charges and negative charges, we have very strong attractions between the cations and the anions. And so the bonds between the atoms are very strong, and that is manifest as the physical property of ionic compounds in terms of having very high melting points. So far, I have been focusing this presentation on covalent bonding theories for individual molecules. If you recall back to my earlier discussion of ionic bonding, we have a three-dimensional network of alternating positive and negative charges, for example, for sodium chloride. Well, in some cases, we can have covalent bonding that extends into networks beyond an individual molecule. And some examples that you can see if you look into your textbooks would be extended carbon covalent bonding networks. And carbon is a really interesting case. If the carbon bonds in two-dimensional sheets, we get graphite. And so we have strong covalent bonding within a sheet, but no covalent bonding between sheets. And therefore the physical manifestation of graphite is that those sheets can shear away and we can use a pencil, for example, to write on the page. However, if the arrangement of electron density around each carbon atom is tetrahedral, that means there are 4 regions of electron density, then we can have a three-dimensional continuous covalent bonding network for carbon. And under those circumstances, we have several examples available to us. One of them is to have diamond. Diamond will just have this three-dimensional covalent network, and diamond is very strong. It's very hard to overcome those bonds. More recently, we've found other variations of carbon-only bonding, and that can be a combination of tetrahedral and trigonal planar bonding around the carbon atoms, and we can get carbon nanotubes, and we can get buckyballs and other sorts of structures that you'll see in your textbooks. Another example of extended three-dimensional covalent bonding networks can involve silicon and oxygen atoms, where, for example, if we have a tetrahedral arrangement of 4 oxygen atoms around each silicon atom, we get this extended network of silica, which is essentially sand, a very hard material, high melting point, very, very strong. Finally, I'd like to talk about metallic bonding. It's no different in an underlying sense to all of the other bonding theories in that it involves the interaction of negatively charged electrons with positively charged nuclei. If you imagine taking a whole bunch of molecules together and squeezing them, the energy levels where they share their valence electrons all get compressed. And in a metal, those compression of energy levels for the valence electrons, not the core electrons, they stay very tightly attached to each atom, but the energy levels for all of the valence electrons become smeared out. The word we use in chemistry is we say that they are delocalized. And delocalized energy levels for the electrons means that they can move about. And a typical model that you will have seen in your chemistry books for a metal is to have the atoms swimming in a sea of electrons. The electrons can move freely between one atom and another because the energy levels between each of the atoms have all been smeared together to form effectively a continuum. And this bonding arrangement where the electrons can move freely about gives metals some unique properties. One of them is that they're obviously high electrical conductors because the electrons can flow through the metal. Another one is that many metals are useful, effective thermal conductors. And finally, we are able to shape metals. Metal workers are able to hammer and change the shape of metals. It's said to be ductile because by moving the atoms around in space within this sea of electron densities, we're not changing the overall energy levels of the system. So a lot of the unique properties of metals that make them different from other materials come from the overall bonding arrangements, but the bonding for metals is intrinsically no different to all the other bonding arrangements. We have negative electrons interacting with positively charged nuclei. And that's really all one needs to know to understand all the different types of bonding available to you in chemistry. We can use the idea of sharing of electrons between atoms, that was the whole concept of covalent bonding that I mentioned earlier, to talk about predicting the shape and the structure of molecules. And a very common and easy to use theory to address this issue is known as Lewis structures, developed by a chemist by the name of Lewis almost 100 years ago. The whole idea of Lewis structures is to pair electrons up and then to have those electrons as either bonding pairs or lone pairs in a molecule. And there are a series of steps that you need to think about when trying to develop a Lewis structure for a molecule. Step 1, count how many valence electrons there are for each atom in the molecule. By valence electrons, I mean the outer electrons. We don't count the core electrons. Let's think of a carbon atom, for example. You would all know from year 11 that the electron configuration for carbon is 1s2, 2s2, 2p2. It is the 2s and the 2p electrons, the outer electrons, that are the valence electrons available to share with other atoms in a molecule. And they're the electrons we want to focus on. So let's count the number of valence electrons. Having determined how many valence electrons there are for each atom in the molecule, we want to determine how many pairs of valence electrons there are, and we can then start to arrange those pairs of electrons around the atoms in order to predict a molecular shape. I'm going to go through an example now to show you how all of these steps work. So let's consider sulfur dioxide, SO2. A sulfur atom has 6 valence electrons. An oxygen atom has 6 valence electrons, and we'd have 2 oxygen atoms in the molecule, so we have a total of 18 valence electrons available for this molecule. We are not counting the core electrons that stay tightly bound around each of the sulfur and the 2 oxygen atoms. A total of 18 valence electrons tells us immediately that we have 9 pairs of valence electrons to account for in this particular molecule. Having determined that we need to account for 9 pairs of valence electrons in the molecule, we need to start to fill those electrons in around the atoms. A useful starting point is to think about the least electronegative atom being in the centre of the molecule. The exception to that rule is when we have hydrogen atoms. They, of course, will always be on the outside, and in a molecule like methane, carbon would be in the centre, even though carbon is more electronegative. But in most cases, the central atom will be the least electronegative atom. From what we've seen earlier in this presentation, that is the sulfur atom. So let's put sulfur in the middle and the oxygens on the outside. What we now want to do is to start to account for the 9 pairs of valence electrons that we have by drawing single bonds between each of the atoms in the molecule. We've accounted now for 1 pair and a second pair, so we have 7 pairs of valence electrons left to account for. A rule of thumb, you will learn this from practice. You can't get around this by just doing it once and applying a simple set of algorithms. But terminal oxygen atoms usually have either 3 lone pairs or 2 lone pairs around them. Usually 2 lone pairs when oxygen's involved in a double bond, or 3 lone pairs when oxygen's involved in a single bond as a terminal atom. So because we have as a starting point 2 sulfur-oxygen single bonds, let's put 3 lone pairs around each electronegative oxygen atom. Now we have accounted for 1, 2, 3, 4, 5, 6, 7, 8 pairs of valence electrons. We have a total of 9 to account for, so we will put the 9th pair on the central sulfur atom. When we look at this structure, we need to see whether or not we have satisfied or violated the octet rule. The octet rule tells us that we should have a total of no more than 8 electrons around each atom. We can see in the oxygen we have 2, 4, 6, 8. So the octet's okay for the oxygen. Over here for this oxygen, 2, 4, 6, 8 electrons. The octet's okay for that. For the sulfur, we have 2, 4, 6. That doesn't seem to be something that we want to worry about too much for the moment because the peripheral atoms are okay, but we might have to come back and revisit it. The next step is to consider the formal charges on the molecule. The formal charge on an atom is the difference between the number of valence electrons that atom would have in a hypothetical isolated state and the number of electrons available to the atom in this shared structure. So let's consider the sulfur atom first. Sulfur would have 6 valence electrons if it was isolated, And if we look at this structure on here on the board, we have 2 electrons in this lone pair, and we share 1 from this bond and 1 from that bond. So there are actually a total of 4 electrons around the sulfur atom in this structure, so we can subtract from that 4 valence electrons, and that would tell us that we have a formal charge of +2. So we would draw +2 on here. If we consider the oxygen atom, each of them are going to be the same. We start off with 6 valence electrons, being the isolated atom to begin with. And then if we look here, we have 2, 4, 6, and we're sharing 1 in this bond, 7. So 6 minus 7 means that we will have valence electrons. We will have a formal charge of -1 on this oxygen atom and -1 on this oxygen atom. What we want to do in this Lewis structure is minimise the number of formal charges on the molecule. This particular structure, we have 3 formal charges, and instinctively that would suggest to me that that's too many. So how might we address the issue? So our current structure for sulfur dioxide has 3 formal charges, -1 on each of the terminal oxygen atoms and +2 on the central carbon atom. If we were to consider moving one of these lone pairs in to share with a bond between the central sulfur and the 2 terminal oxygen atoms, we would now have a structure that looks like 2 sulfur oxygen double bonds, 2 lone pairs around the terminal oxygens, and now a single lone pair remaining on the central sulfur. If we look at the formal charges now, let's start with the sulfur. We know we have 6 valence electrons in an isolated sulfur atom. Now we have 2, 1 from this bond, 1 from that bond, which is 4, 1 from that bond, 1 from that bond, which is 6. 6 minus 6 is 0. We have a neutral sulfur. Let's look at the oxygen atoms. We have 2, 4, 1 from this bond, 1 from that bond, which is 6. 6 minus 6 is 0, so we have a structure that has no formal charges on it. We have minimised the number of formal charges, and this is the predicted Lewis dot structure for sulfur dioxide. The Lewis structure model of chemical bonding is really useful for being able to determine how many pairs of valence electrons we have in a molecule and the overall geometric arrangement of molecules on a 2-dimensional page. As I mentioned earlier, one of the important points to check for in a valid Lewis dot structure, apart from minimising the number of formal charges, is to see whether an octet has been satisfied. And we can see with our terminal oxygen atoms that we have 2, 4, 6, 8 pairs, a total number of electrons around each oxygen atom. So we have satisfied the octet. In your Year 12 curriculum, you only need to worry about the octet. So if we look at the central sulfur, we can see that there are actually more than 8 electrons. The octet theory doesn't always apply, and that can confuse many students. So this particular molecular example is one that you're unlikely to see in an examination context, but the example I went through shows you how to go about allocating all of those 9 pairs of valence electrons available to the molecule. 1, 2, 3, 4, 5, 6, 7, 8, and the lone pair 9. What this theory doesn't show you, or this Lewis structure theory doesn't show you, is the 3-dimensional arrangement of electron densities around a molecule. And to do that, we invoke a model known as VESPR, which is an acronym for Valence Shell Electron Pair Repulsion. And what the VSEPR model requires you to do is to first draw a Lewis structure for a molecule and then look for the number of regions of electron density around the central molecule. Not the number of bonds, not the type of bond, but the number of regions of electron density. So if we look at our SO2 example, the central sulfur atom has a region of electron density for one sulfur-oxygen bonding region. It does not matter whether it's a single or a double bond. It's one region of electron density. We have a second region of electron density for the other sulfur-oxygen bond. And then finally, we have a third region of electron density for the lone pair on the central sulfur atom. So the key thing about VSEPR is to count the number of regions of electron density around the central atom. And now we can look at a simple table of information to work out what will be the overall geometric arrangement of electron density in 3 dimensions around the central atom. If we had 2 regions of electron density, we would have a linear arrangement of electrons. 3 regions of electron density, which is what we have for our sulfur dioxide molecule, we have a trigonal planar arrangement. 4 regions of electron density, and we would say that the arrangement of electrons around the central atom is tetrahedral. If we have 5 regions, we have a funny word here, trigonal bipyramidal. You would all know that a pyramid in Egypt has a square base. So a pyramid has a square base and it comes up to a point. That's called a pyramid. If you have a triangle base and it comes up to a pyramid, that's called a trigonal pyramid. And a trigonal bipyramidal structure means that we have a trigonal pyramid of electron density above the central atom and another one below the central atom. Finally, if we have 6 regions of electron density around our central atom, we would have what's known as an octahedral arrangement of electron density. In our sulfur dioxide example, we found that there were 3 regions of electron density. So we would say that the geometric arrangement of electrons around that sulfur atom is trigonal planar. Trigonal planar. However, the shape of the molecule is not trigonal planar. This non-bonding pair of electrons, this lone pair here, contributes to the arrangement of the electron density, but it does not contribute to the overall shape of the molecule, and the shape of the molecule is therefore shape equals bent, B-E-N-T. Doesn't sound very technical, but that's the word we use to describe the shape of sulfur dioxide. We discount the lone pairs for the shape of the molecule, but the lone pairs are critically important for determining the geometric arrangement of electron density around the central atom. Having determined the shape of a molecule, it's important to be able to predict some of the overall molecular properties of a molecule. For example, is that molecule polar or non-polar? I'll show in the next video that the answer to that question plays a fundamental role on some of the intermolecular forces and therefore the physical properties of that molecule. So let's build up to understanding what it means to be a polar or a non-polar molecule. We come back to the concept of electronegativity that I talked about earlier. We have electronegative elements in the upper right of the periodic table, and the left-hand side of the periodic table has less electronegative elements. So if we were to draw a covalent representation of the HF bond, we would have an electropositive H atom and an electronegative F atom. That unequal sharing of electron density that I talked about earlier can be represented by a simple diagram I've drawn in green here, which is a bond moment, B-O-N-D, moment. What the bond moment representation is showing us is that the arrow is pointing to the negative end of the bond, and to help us remember that, we draw a little vertical line at the opposite end of the arrow to try and represent a plus sign. So we've got a bond moment to represent unequal sharing of electron density pointing towards the negative element. In our sulfur-oxygen bonds that we talked about earlier, we would have bond moments going from the less electronegative sulfur to the more electronegative oxygen with the positive sign at the more positive end. So let's consider carbon dioxide. I've drawn the Lewis structure for carbon dioxide on the board here. We can see that we have 1, 2, 3, 4, a total of 8 electrons around this oxygen, so the octet's satisfied. The octet is satisfied on that oxygen, and we have 1, 2, 3, 4 pairs, 8 electrons around the central carbon atom. No lone pairs on the carbon atom. However, each of these bonds is polar. Carbon is less electronegative than oxygen, so we can draw a bond moment for that particular carbon-oxygen bond as I've represented on the board. The other carbon-oxygen bond has a bond moment that's equal and opposite in magnitude. So these two bond moments will cancel out. And I'll come back to that concept in a moment. If I was to draw my sulfur dioxide molecule from earlier on, we can see again that we have a bond moment for one sulfur-oxygen bond pointing as shown, and the bond moment for the other sulfur-oxygen bond as shown. These two bond moments do not cancel each other out in a vector sense. They are both pointing in the same direction. So, overall, if I change pen, we find that the bond moments here cancel. Bond moments cancel, and the molecule in CO2 has no net dipole moment. It is said to be non-polar because it has no dipole moment. In our SO2 example, these two individual bond moments are pointing generally in the same direction, so we have a net dipole moment, and the molecule is said to be polar.
Hi guys, hopefully that helped you out. If you still have any issues with chemistry in general, just go to the links that we've given you or ask your chem teacher, they're probably your best resource. Good luck with exams and hopefully we'll see you here at Curtin.